Good day, everyone. In this video, we're going to be talking about exponentials and logarithmic. All right, in this lesson, we are going to write exponents into logarithms. I am going to post a video about logarithmic functions in decimals, or I'll probably do regular functions. All right. Also, not now, but later, I'm going to show you how to solve equations using logarithms. All right? Probably I'm not going to do that. So don't worry about the solving equation using logarithms. I may or may not do that, but I'll let you know when. All right. Before we get into our lesson, we must talk about our history. Now, we're going to talk about mathematicians. All right. Remember, mathematics is the technique to teach, learn, and manage reality by ciphering, counting, measuring, classifying, ordering, inferring, and modeling patterns arising in the environment. So y'all listen up. So in this definition of mathematics, I kind of shortened this up a little bit. I kind of changed up some of the words. It was just only this these few words right here, but everything else is the same. Well, actually, I didn't really change anything up. It looks like I did, but no, I didn't. Definition is still the same. So, on your test, I may give you an assignment to talk about the precise definition of mathematics. And in that assignment, you have to break down these definitions, these words, and know what this definition truly means. Before we talk about historians, people, I want you guys to understand how even you yourself set out the precise definition of mathematics. All of us in every part of the world use counting. We all count. That's what we do. That's our thing. We all count. Ciphering. I'm gonna show you that so you can see what ciphering is truly about. But everything else, it's common. We love to, infer. You want to learn what that is. And in our last lesson, we modeled patterns arising in the environment. All right? So let me introduce you to these two people. One of them is not a mathematician. I would love to introduce you to Miss Josephine Baker. Very stunning and very beautiful. Now, she was around during the 1940s. She was born in 1917 in St. Louis. During that time, Black lives did not matter. There was a race riot situation where whites got murdered a bunch of black folks. So many black folks got hurt in the race riot. So at a young age, she got married at 14 too. But she left the U.S. She was a dancer. But of course, in America, black dancers don't go far in life. So what she did, she left for Europe. Europe was a place where black was all right. You still had problems, but it was okay for you to still be there. But during that time, in her for her to be accepted, she has to lighten up her color. So that's why in this picture she looks, light, but she's a black lady. All right. So she was the first black spy. She wasn't just a dancer and a singer, but she was the first black spy. as she satisfied the precise definition of mathematics as the first black spy to use rational numbers to cipher information in her song sheets to liberate France under Nazi rules. Alright? On your test, you need to know her well. There are some movies there that you can look to know about her. She was a remarkable lady. She was ahead of her time. It was her who showed the world that black can be beautiful and black can be gorgeous. So it's a lot of respect we have to put to her. Now, I just showed you a dancer who satisfied the precise definition of mathematics, and she's not even a mathematician. Next, I would love to introduce you to Dr. Gladys Mae West. This darling sweetheart, she's still living today. She satisfied the precise definition of mathematics by using her geometrical techniques to model patterns arising in our environment. I don't know why I spelled out, but our. Let me fix that. Put an R right there. To create the GPS. So, not too long ago, I would say about in the 2000s when I was born, 2007. Most of y'all was born around that time. Um, During that time, there was not such thing as a GPS. Common to everybody. Let me correct. Common to everybody. You know, the Google Maps, the maps on your phone, the maps on your GPS in your car. It was this beautiful lady who created it. She used all the geometry skills that I have been teaching you, and then some, to create the GPS system. So I know all the time you kids say, I ain't gonna use math, blah, 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 this, blase, blase, blase. But there are people who use math to do wonderful things. I need for you guys to understand, you know, that math is just could do things. You could do things for math that could benefit the generation after you to make the world a better place. These two ladies were the two. And Dr. Gladys Mae West, she is a mathematician. And I believe she loves to garden too. So you could look her up too and learn something new. I may even make it an assignment to look her up. I'm going to continue to send y'all more information and talk about these people who satisfy the precise definition of mathematics to make the world a better place. All right, so let's talk about logarithmic graphs. And of course, inverses. I wonder why am I saying the word inverses here? So let's dive deep into it. Why not bring exponential functions into this if I'm dealing with logarithmic functions? I used the word inverse. I wonder what connection would that be? Take a moment and find it out for me right fast. Why would I talk about exponential functions when I'm supposed to be talking about logarithmic functions? But I used the word inverse. Inverses. All right. Whatever answer you got, hold on to it for a second. So let's review an exponential function. A basic exponential function has a domain of all real numbers. It doesn't matter what exponential function you have. It could be something crazy as 5x minus 1 plus 3. Guess what? Your domain will always, forevermore, be all real numbers. Your range is going to be of a basic exponential function of 0 to infinity. Now, this will change based on the exponential function. So if you have like 3 to the power of x minus 1 or something like that, your range is going to change. It won't be 0 no more. All right. You will not have an x-intercept. Typically, you will not have an x-intercept for the exponential functions. Rare occasions, on rare occasions that happen. Rare. So I was going to say rare. But most cases you don't. However, you is always forevermore going to have a y-intercept. But a basic exponential function has a y-intercept of 0. But the y-intercept will change depending on your functions. But by that same definition, you're going to have an asymptote. Now, I usually like to define my asymptote of saying that it cannot equal 0 because if it equals 0, it's going to be undefined. But you're going to see some situation where they're going to say y is 0 because they're looking at it differently. So, I don't know. I may allow you to say your asymptote as y equals, but I don't know. I'm probably going to tell you to use y cannot equal 0. I'm probably going to be grading you on that because the asymptote is drawn in line where the graph gets close to but never touches. So, and because it's being y, it has a horizontal asymptote. Horizontal for exponential functions. Horizontal. All right. Logarithmic. Now, a logarithmic function, a basic logarithmic function, has a domain of 0 to infinity. So that means that your domain will change depending on the kind of logarithmic function. However, your range is always, forevermore, stay the same. All right? Our next bit, it will have an x-intercept. An x-intercept equals 0. All right? An x-intercept equals 0. All right? You won't have a y-intercept. You won't have a y-intercept. It will rarely happen. Rarely will it happen. All right? And it will have an x not equals 0 as an asymptote. So that means it has a vertical asymptote. It has a vertical asymptote. Again, I did not draw that line well, but yeah, I get the point. Remember, asymptote is where the graph gets close to, but never touches. All right. So I want you to graph these functions. When you graph these functions, I want you to discuss how these transformations, because all these are transformations from the original, how these affect those characteristics of each. Like, go back to the video where I talk about a basic logarithmic function. I want you to compare and contrast this function that you are right here to the basic logarithmic parent function that I have discussed. And you're going to do the same thing here. And then for exponential functions, you're going to talk about the exponential basic characteristic that I have talked about. I want you to determine how these transformations affect the characteristics. And the same here, I just want you to take notes to just describe how the transformations affect the characteristics. All right, so I asked you a question earlier. By now, you should know the answer to this. These are my inverses. And remember, a final example of an inverse, if I could switch my coordinates to 0, 1, to 1, 0, I have an inverse. If I have 1/3, -1, if I could flip those coordinates into -1, 1/3, I do have an inverse. So my exponential function, y equals 3 to the power of x, is the inverse of log base x. All right. So here's some details that we have to look at. So every exponential function of the form b to the power of x, and again, b is your base, b is a positive real number other than 1. And its inverse function can be noted as log base b x. So log b of x is how you say that. And the inverse is called a logarithmic function with base b. So when we're saying b, we're just saying, like I said, a real number. So, and I'll explain the details a little bit more to you momentarily. All right, so let's dive into exponents to logarithms. Now, there's some information that I left out in the previous slide, but you're going to see those details coming. And we're going to learn how to rewrite exponents to logarithms and vice versa. All right, exponents. Consider a base and an exponent. And we know exponents is repeated multiplication because 5 to the power of 3 is saying 5 times 5 times 5. And that's going to be 125. All right, so here's some details of the exponential function. So you have f of x equals b to the power of x. But b has to be greater than 0, and b cannot equals 1. B cannot equals 1. Okay? This is very, very, very critical right here. Because this defines what an exponential function is. So this is telling you that you cannot have a base of 1 to any exponent, because at the end of the day, if you do that, if your base is 1, it doesn't matter what exponent you get, you're just going to get 1. If you say 1 to the power of negative 5, guess what? It's still going to be just 1. So that's the reason why we don't want our base to be 1. Alright? Also, a base cannot equal 0, because if it's 0, of course it's undefined. So moving on, the exponential function has an alternative form known as e to the x. E to the x, it is your natural exponential function. Take close note to that, alright? Take very close note to that. Alright? The next thing I want to talk to you guys is the third form of exponential functions. It has another number times your base time to the power of x. And the rules still apply similar to the original function, bx. So a times b to the power x, a cannot equal 0, because if it equals 0, it's going to turn everything to 0. B got to be greater than 0, and also cannot be 1. Your base, like I said, is greater than 1, but B can be between 0 and 1. So if I'm talking between 0 and 1, what am I talking about? I'm talking about a rational number, which we use for the letter Q as rational number. So it could be 1/3, because 1/3 is still between 0 and 1. So any proper rational number could be in that definition. All right. So here's some examples. So you see how this is 2 right here? The base is 2, and then your base is 1/2. That's part of an exponential function regardless. So when you have anything greater than 1, that is a real number, or an integer in this case. This is called a growth function. This is considered to be a growth function. Okay? When you see a rational number, that is going to be called a decay function. This is a decay function. Okay? I want you to try something for me. So 16. Break that into your prime factorization for me. Use your prime factorization and break that down for me, please. Pause the video and just try it. Alright. Welcome back. When you saw 16, your prime factorization should have been 2 to the power of 4, because 16, when you break that down, is going to be 8 and 2. And then you could break that down to 4 and 2. And then 2 times 2. Alright? And we put that in exponential form, we get 2 to the power of 4. Because 2 is repeating 4 times. It has a repeating multiplication as 4 times. 4 times. So that's why it's 2 to the power of 4. Alright? So, that's the exponential form of this. But the logarithmic form, before I tell you, is asking this question. So, we did our prime factorization. How many 2's did it take for us to get to 16? How many 2's did it take for us to get to 16? It took 4 of them. So, logarithms are pretty much trying to identify how many times did this repeat to get to this guy right here. So, logarithms are asking you how many 2's repeated to give me 16, and that's 4. Because 2 to the power of 4 is 16. Alright, now with that being said, let's give us some clarity about a logarithm. So, when you think of a logarithm, as I have stated before, you're trying to figure out how many of one number multiplied together to make another number. So, here's a question for you. How many 2's multiplied together gives you 8? So, how many 2's multiplied together gives you 8? How many 2's? So the answer is 2 times 2 times 2 is 8. So we have to multiply 3 of those 2's to give us 8. Now be careful, because I know many of you guys like to say, you said 2 times 3. I'm not saying 2 times 3 to give me 8. I'm asking you for repeated multiplication. So what I was saying is, how many times must 2 repeat itself, repeated multiplication, gives you 8? How many 2's must repeat multiply that gives you 8? And the answer is 3. And so that's why we write it as log 8, 3, because you're trying to figure out how many 2's did it take. You're trying to figure out that missing exponent. And once you get 3, that's it. All right. So, why don't you pause the video and try this out for yourself? I want you to ask yourself this question. 8 to what power gives you 64? 8 to what power gives you 64? Pause the video and try it. Alright, welcome back. I trust that you have worked this problem out and you tried it yourself. You didn't photomath, you didn't lie to yourself, you did it, from the dome. Your answer is going to be 2 because 8 squared is 64. So why don't you try the next one? Pause it and try it right quick. Alright, I trust that you kept it 100, you tried it. So the question is, when you evaluate logarithms, 4 to what power gives you 64? And the answer to that is 3. Alright, so here's a unique situation I want you to take note of. This is very important about logarithms. So, logs have an invisible base of 10. So when you see log by itself, and you see like log x, you see no base underneath, right? When that happens, that means that you have a base of 10. So let's look at this example right here. So you see log, and there's no base. Well, it has a base of 10, but it's invisible. So 10 to what power gives you 100? And the answer is going to be 2. All right? All right. So here's some information that we have to define. The logarithm of x with base b is defined as log base x equals y if and only if base to the power of y equals x, where x is greater than 0 and b is greater than 0, and b cannot equal 1. So let me repeat that again just in case I got a little tongue-tied there. So where x has to be greater than 0, b, your base, has to be greater than 0, and your base cannot equal 1. A logarithm, and sometimes I spell that with a H-I-M versus H-M, logarithm, its alternative form is ln. So I know you guys are used to log bx. This is called your common log. All right? When you have your log without a base, you could call it your base 10. That's your base 10. Or you could call it your uncommon. But when you have log natural log ln x or ln, that is your natural log. So we can conclude that logarithms and exponents, exponentials and logarithmic functions, that have each 3 different forms to deal with. Well, actually, logarithms have 3, exponentials have 2. I'm sorry. Exponential has 2 forms. Logarithm has 3. No, I'm tripping. I was right the first time. So they each has 3. And if you need to understand what I'm talking about, go back and replay the video and see the forms of exponential functions. All right. So the next thing we're going to do, we're going to rewrite logarithms into exponents and vice versa. For example, if I have log let's use an uncommon log to 1000. So what the answer is going to be, remember, if you don't see a base in the bottom of this, you should know that to be has an invisible base of 10. So it's saying 10 to what power gives you 1000. And the answer of that should be just 3. And the answer there is 3. So we rewrote it to logarithms to exponential forms, from exponential to logarithms. So remember, your base is going to be at the bottom for log, but that base is going to be right here. It's going to be your big number. Your exponent is on the outside of your log, but it's in the inside. Your argument is going to be in the inside, but the outside there. So pause this video, just kind of think on it, and let's move on. Pause the video, look at this, and when you're ready, let's move on. Alright, so here's an easy example. So I wrote the exponential form of 7 to the power of 0 equals 1. What I'm trying to do is write it into logarithmic form. So what is missing here? This box is telling me I'm missing something. Pause the video for a quick second and find out. Alright, welcome back. Did you get 7 to be your base? Because 7 to the power of 1 is 0. Splendid. Good job. You got this. Alright. So I want you to try this one on your own too. Pause and try it. Alright. Welcome back. If you have read the pause the video, read the directions, and tried this out, you are awesome. And did you get log 8? Log base 8? With the argument of 8 equals 1. If you did that, awesome. Alright. So we still run exponential to logarithms. So what's missing? This is going to be 1. Because 4 to the power of 1 is 4. So this is your log to your exponential form. And then this is from exponential form to logarithmic form. Again, it's just putting stuff in place and it should be fine. Alright, now I want you to pause this video and see what's up. Pause the video and try it. Alright, welcome back. Did you get the base to be 10 here? Because I cannot draw on this. Because this does not have a base. So it has an invisible base of 10. So 10 to the power of 2 is 100. 10 to what power gives you 100, which is 2. So logarithmic to exponential form, and from exponential form to logarithmic. It's pretty easy. It's not much of a challenge. Alright. Pause the video and try this one out too. Alright, getting back to it. So, you realize that you need that to be 3. Because this is invisible, so it has a log of 10 by itself. So what's the point of all about logarithmics? The reason why we deal with logarithms is because, personally to me, an earthquake. An earthquake destroyed my background. This is an earthquake that took place in 2010, and this took place in Haiti. But if you look at it, it looks like it took place in New Orleans. But this is Haiti, 2010. So destroyed my family's home. So we deal with logarithms to measure the scale of earthquakes. This is a picture of sound waves. We're going to be dealing with that too, with logarithms. And then we're going to be dealing with the pH scale of logarithms. So, from base to acidities. So think about acid reflux and all of that. I need for you guys to go in and think about that. So we're going to be working on that when we get a moment. All right, y'all. Not bad. I'm going to post other videos of exponential and logarithms in detail. They will be posted and you are responsible for them as well.